In this video, we're going to look at the quotient rule. And the quotient rule for derivatives helps me figure out how to evaluate the derivative with respect to x of the quotient of two functions, f of x divided by g of x. Now, when students first see this, they oftentimes want to jump to this being the derivative of f of x divided by the derivative of g of x, and making it that simple. Unfortunately, this is not the case. Quotient rule is actually going to be the bottom function, g of x, multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator all over the denominator squared. So just a little example to see here before we jump into a proof. If I were considering the derivative with respect to x of something as simple as x to the fifth over x squared, well, we know from algebra that x to the fifth divided by x squared is x cubed, and the derivative with respect to x of x cubed is going to be 3x squared. So we know this is the answer we want. If I tried this method, so equals with a question mark, the derivative of x to the fifth is 5x to the fourth. The derivative of x squared is 2x, and this would give me 5 halves x cubed, which is clearly not the right answer. But if I used my rule here, low times the derivative of the high, so I have x squared times the derivative of the upper, which is 5x to the fourth, minus high d low, upper divided by, or times the derivative of the lower, so x to the fifth times 2x, all divided by the lower squared, so that's going to be x squared squared. Sending this through, I get 5x to the sixth minus 2x to the sixth, all divided by x to the fourth. 5 minus 2 gives me 3x to the sixth over x to the fourth, and subtracting the exponents gives me 3x squared. Alright, next up, we're going to see a proof. If you want to skip the proof, look in the description. You can click on the various times to skip on to the next example. But here we go. So, in here, a proof. I'm going to start with this side. So the derivative with respect to x of f of x divided by g of x will equal, of course, the limit of the difference quotient. So the limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. And whenever I see fractions in a fraction, I'm going to multiply by the least common denominator in this numerator to get rid of the fractions in a fraction. So I'll multiply by the top, g of x plus h times g of x. And if I multiply it to the top, I need to multiply it to the bottom. So that I'm just multiplying by a special form of 1. That doesn't change anything in the problem. And as I multiply it through, what happens is this. So equals limit as h approaches 0 when I multiply g of x plus h times g of x to this, the g of x plus h's cancel, and I'm left with f of x plus h times g of x. When I multiply g of x plus h times g of x to this one, I have a minus. The g of x is canceled, so I have f of x times g of x plus h. I'll have this over h here. And I'm just going to bring this over here as 1 over g of x plus h times g of x. Now a few things I can do here. So this right here, as h approaches 0, g of x plus h approaches g of x, so that's going to be a 1 over g of x squared. Over here, I need to figure out what to do. So I'll bring the limit in, limit as h approaches 0. I'll have f of x plus h, g of x. I'll leave some space to fill in a certain term, and I'll have minus f of x, g of x plus h, all over h. The term I'm going to fill in is going to be this. I'll have minus f of x, g of x, plus f of x, g of x. And I can do this because when I subtract and add the same thing, it's like adding on 0. It doesn't change anything. And the reason I do this is the following. So in here, I'm running short on room, so I'm going to sort of skip the step here. I can factor out a g of x here, and I'll be left with a different quotient of f of x plus h minus f of x. So that's going to be times the derivative with respect to x of f of x. In here, I can factor out a negative f of x. And if I factor out the negative f of x, I'll have g of x plus h minus g of x over h. So that's going to be the derivative of g of x. And notice, so the limit of this over h is what gave me the derivatives, but I still have this g of x squared in the denominator, and that gets me to where I wanted. So I skipped a little step there just for space's sake, but that's the idea for the proof of this. So let's see another example here. All right, recall that I want to do low times the derivative of the high minus high times the derivative of low, all over low squared. So this will equal, I have 2x squared minus 5x times the derivative of the upper, which is 1, minus the upper, the numerator, x plus 3, times the derivative of the denominator, which is 4x minus 5, all over 2x squared minus 5x all squared. So in here, I'm going to distribute through the 1. I get 2x squared minus 5x. I'll multiply this through, so I'll get x times 4x is, so I have a minus 4x squared. X times negative 5 is plus 5x. 3 times 4 with that minus gives me minus 12x. And 3 times negative 5 gives me negative 15. Times that negative 1 is plus 15. I'm not going to expand this out because if anything cancels, I'm going to want it in the factored form anyway. So 2x squared minus 5x all squared. And I can combine some like terms, so I have 2x squared minus 4x squared, which is negative 2x squared. I have negative 5x plus 5x minus 12x. And I have a plus 15. And that's all going to be over 2x squared minus 5x squared. All right, I hope that helped out. Feel free to comment below if you have any questions.